Good day everyone, I'm Cadet Pulpin Sitikuman and we are the Group 10. We are going to discuss the manual radar plotting. So, for the course outcome, working knowledge of the manual radar plotting, and for the learning outcome, demonstrate working knowledge of the manual radar plotting for safe navigation. And the importance of this topic is the students will have a working knowledge of the procedures of safe navigation and collision avoidance using manual radar plotting. So, manual radar plotting. Safe navigation is a basic task of each navigator while conducting a vessel. To achieve this goal, he or she has to possess different skills such as the ability to identify moving targets, gather various information to assess navigational situations, navigate according to the rules of the road, and be able to control the vessel's movement by using the helm and main engine. Although navigational technologies are improving, there are still many accidents caused by human error.
Collision avoidance is one of the prime skills an officer of the watch or OOW must obtain. It has a basic technique achieved by knowledge of the rules of the road, COLREG, Convention on the International Regulations for Preventing Collision at Sea, communication and maneuvering. Unlike disasters such as grounding, fire, or flooding of vessel, collision at sea are rarely caused by act of or technical error. In other way, the collision avoidance solution is defined in this analysis rather broadly. The focus is not on which action should be taken, example, change waypoint or speed, but not on the failure or success, on the identification of this safe action and its implementation. Based on accident analysis, the reason for collision are mostly human errors, insufficient lookout, visual or by radar, insufficient adjustment of the radar due to the weather condition, inadequate speed of the vessel according to the navigational situations, lack of bridge team and bridge resources management, superficial communication among bridge team members and or with a pilot, excessive reliance on the navigational equipment, lack of available crew on the bridge, incorrect interpretation of navigational situations, situation awareness, disregard and ignorance of the rules of the road, Distel 2005, Gile 2007. Human error can occur in many forms and can lead to fatal situations. There have been reports of maritime accidents that have occurred solely due to human errors, from small fires that can lead to a big explosion, to full-on collision. The scale of accidents that can result from human errors is uncomfortably large. The classic example of this would be grounding of Torrey Canyon that occur in broad daylight with seemingly no reason to have met that fate, but it still did so just because the captain decided to take an unconventional path. Manual radar plotting and ARPA calculation. The collision avoidance problem was in the past solved by the method of manual radar plotting, which was in use by seafarers until the implementation of the ARPA calculator on maritime radar. Manual radar plotting is a method using vector algebra for calculating parameters such as CPA and TCPA. These are main parameters for collision probability assessment with the target vessel or fixed object, and although this method is no longer in use by navigators, it is part of the STCW model course for seafarer certification. ARPA provides all the necessary information for the radar user, and it helps in saving a lot of critical time from observing a target to finding the data using radar plotting and calculation. Collision avoidance and detection data is thus readily available to the radar user in no time, just by the click on the target. ARPA takes feed of the own ship's course and speed and target's course and speed, and calculate the collision avoidance data and simplify the needs for the users to calculate the data themselves. ARPA provides various other additional features and control as well.
Based on this method, the ARPA calculator was developed. Almost all the marine radars nowadays are ARPA, which on the basis vessels movements calculate the essential navigational parameters. So there are factors which the relative and true course of the target vessel, relative true speed of the target's vessel, CPA, the CPA, distance to the target's vessel. With manual radar plotting, the position of the target vessels, the distance, and the bearing was transferred in time intervals on the radar diagram or maneuvering board. So we will have a tutorial on how to find targets and calculate the TCPA, CPA for next slides.
Hi, my name is Kadeter Marcusef and this is my report. With two position of the target vessel in 3, 6, 12, MES OOW has been able to determine the relative course of the vessel's approach. Based on that own and relative course, the navigator obtains the true course of the target vessel. Vector velocity triangle, her speed, CPA, and TCPA. If the CPA were less than the desired vessel safety domain, the OOW began to design the path of collision avoidance. And in every navigation, there are three ways to avoid the target vessel, and it is known as avoidance with change of course, used in this paper. Next is avoidance with change of speed, and last is the avoidance with change of speed and course. When the OOW has determined the size of a vessel safety domain 1, which must satisfy safety requirements defined by the master or company, she must determine at what distance from the target vessels a change of course will begin. In accordance with the Colruyt rules, this distance is called the action point or AP, from which the tangent line is dragged to the circle of the safe vessel domain. Then the tangent line is transferred parallel to a 6-minute position of the observation of the relative vector, and thus produce a new relative movement of the vessel and a new avoidance course to the starboard. So in this figure, the R is the relative vector or the target vessel, T is the time vector, and AP action point, CPA closest point of approach, TCPA time to closest point of approach. Then you can see the CPA and the CPA at the middle, and the ship safety domain 1 nautical miles, then the open course and the avoiding course. Next, if we are in the open sea and have a good visibility, our estimated is the not less than 1 nautical miles during the day, and if night or heavy seas, the estimated is not less than 2 nautical miles. In restricted visibility, the CPA must be greater than 2 nautical miles. In this article, a vessel safety domain or CPA limit is determined by the author, and it is at least 1 nautical mile. Next, how is radar plot done? In radar plotting, we use the relative approach of the targets. It is the easiest way to find the CPA of the targets, but the issue with the relative approach is that we do not know with certainty the angle at which the target vessel approaching.
Good day, I'm the Cadet Jeff Tigas, and for today's video, I will demonstrate the basic manual radar plotting. So first thing, we need to know where the ship course. So in a given, our ship's course is in 80 degrees. So this is our own shapes course. So here we need to find the DRM, the SRM, CPA, CPA bearing, TCPA, and the TTS. So first we need to find the DRM. So to find the DRM, we just need, first thing to do is to know the target. So we have a target in a given. We're given that the first observation, the target was in the 20 degrees in 9 nautical miles. So since this is a 2 scale plotting sheet, 2, 4, 6, 8. So somewhere here, the 9. So since we're in 20 degrees, 9. Or we can calculate this since I don't have a compass divider. 9. And the target's observation in second, the interval is 6 minutes. So in 6 minutes, the target was in 21 degrees and in 8 nautical miles. So by 5, 21 somewhere here. Here. So the DRM, we need to so this is the RML, or the relative motion line. So to get the DRM, we just need to put this in our center of our plotting sheet. So the DRM, we get 191 degrees. RM 191 degrees. So the next step, we need to find the SRM, or speed relative motion. So to get speed relative motion, we have a formula of speed equals distance over time. SRM equals distance over time. So the distance, it talks about the distance from R to M. So I forget. We just need to put R and M. The first observer is R, and the second is M. So we just need to know the distance of these two. So approximately, the distance is in 1 nautical miles over the time interval of the target. So 6 minutes interval, 6 minutes. But we need to transpose this into hours. So 6 minutes, 6 times 0.6, 6 times 60 equals 0.1 hours. So to compute, 1 divided 0.1 is equal to, we get the SRM, 10 knots. So this is our speeds. So we get the SRM. The second thing to do is to get the CPA. So CPA is in here. From this RML to DRM, the center of this is the CPA. So we just need to put a 90 degrees angle from the center of this, of the DRM and BRM line. So this is our CPA. This line, we need to get so we get our CPA is 1.5 nautical miles. 1.5 nautical miles. Then the next is the CPA bearing. So this is so easy. We just need to extend the line of this CPA what we get earlier. So our CPA bearing is 101 degrees. Then the TCPA, to get TCPA, we have a formula, the distance over SRM, or speed. So the distance, times 60 today. So the distance here is distance to R to CPA. So the first observation to CPA here. So I advise that you have a compass divider for easy getting the distance of this. So the distance from R to CPA is 8.9 nautical miles over the SRM. So earlier we get the SRM 10 knots. We just need to put here times 60. So we need to multiply it by 60 because we need to obtain the minutes or the time. So to compute this, just need to 8.9 divide 10 knots times 60. The answer is 53.4 minutes. So the TCPA is 53.4 minutes. This is where the one. So that's how to get the TCPA. So the next step, we need to find the TTS and the TTC. So TTS stands for the targets true speed, and the TTC targets true course. So to find that, for the TTS, we need to find the E. So E, since our ship speed is 80 knots and the time interval of the observer's position is 6 minutes, we multiply 18 knots to 6 minutes. So 6 minutes, we need to transpose that into R. So 6 minutes equals to 0.1. So 18 times 0.1, so the answer is 1.8. So we need somewhere here. So E is reciprocal from our own ship's course. So we get 1.8. 1.8. So we label it to E. So A to R is for our own ship, the own ship. Then the E to M is for the target. So TTS was distance over time. So the distance we get earlier, the 1.8 nautical miles. We multiply it by 0.1 or the interval from R to M. So the TTS, the target's true speed is 18 knots. Then to find the TTC, we just need to transfer this line to the center of this plotting sheet from E to M. So we get TTC of 115 degrees. So now we get the DRM, the SRM, the CPA bearing, TCPA, and the TTS and the TTC.